don't really care if you cry. I don't really should've never lied. What's going on, my party people? Today, if you can believe it, it's going to be the last day of studying for finals, okay? Not ever in our entire lives. We still got one more year of that, but it's our last day of studying for finals for the semester, because tomorrow I have my last final at 8 a.m. That's right, 8 a.m. You've heard me correctly. 8 in the morning. I have my last final from 8 to 11. Now, I took my real analysis final today, and I felt actually like I know that I didn't get a 100. I didn't ace it, but I felt pretty confident. Every question, I kind of knew what to do, and I knew what I couldn't do. So I just wrote down what I wrote down, and yeah, I was the first one to finish, which may or may not be a good thing because I'm sure there are people in that class who are fucking cracked at real analysis. So, I mean, I don't know. I guess it goes to show I'm confident in what I know and what I don't know. I will never have to have this ever again, so I can probably just throw these away, honest to God. Should we burn it? Should we burn it? No, let's not burn it right now. Let's just put it... I don't know where to put it. I don't... put it there for now. Yeah, so... we gotta study for solid state. What that will entail is going through the past... going through the practice final one more time. Really taking our time with the Lakau block function, the type binding model. I don't quite get that completely yet. Though I have a couple of images. I was working it out with a friend, and they are an expert on the Lakau model stuff. So I'm thinking, okay, I'm just going to follow their lead on it. I don't really care if you cry. Oh no, really, you should have never lied. I'm gonna actually airdrop it to my computer. The chalkboard that we were working on. Put it here, open it up. I'll just slot it here. This is some of the work that we were doing. You can see my work completely gave up. But then his work was better. So let's walk through this. We'll walk through it one more time. We might even just review a phonon problem, which would be something like... that's not the right subject. This is also type binding, actually. I'm not even gonna lie. I'm just feeling fucking burnt out, brother. I guess we'll look at this. I don't know. But yeah, okay. So let's start on some music. Some music. A little bit of Minecraft chill for the boys. Am I even sharing my screen? No, I'm not. There we go. So. Oh, I'm playing it through my speakers. What a silly guy I am. Okay, let's do our tried and true little review thing. Looking through emails. Okay, that's all the emails. Boom. Okay, let's go through our tried and true. Any trepidations that we're feeling going into this? I don't know. I'm just fucking exhausted. I'm very tired. Yeah, I'm just tired. Okay. What else is there to say? I guess considering I'm tired, let's just tackle the hardest thing first. I guess, which is a tight binding model. So, fuck, I got so much things on this table right now. I've got so many things on this table. Okay. Put that up. Guys, I cannot wait. I cannot wait until my finals are over, but I cannot put... What is it? Can't put the lead before the horse or some stupid shit like that? Was some stupid saying. Can't count all of my eggs in one basket before they've hatched. Okay. Tight binding model. Write down the general formula for an least common atomic orbital. Block function in terms of atomic orbitals, phi r minus r. Here r is that. Okay, so the locale block function is given as psi k is going to be equal to 1 over square root of n, some summation from n m e to the I k dot r and m phi r minus r. I guess it's over r in general, not over nm. Because nm is not a linear combination of atomic orbitals, not least common. State whether or not we need to solve a matrix equation in each of the 3 following scenarios. A one-dimensional crystal with 1 orbital in each unit cell. Because we have 1 orbital, we don't really need to. A 2-dimensional crystal with 1 orbital in each unit cell. Because we have 1 orbital, I don't think we'll need to. A 1-dimensional crystal with 2 orbitals in each cell, I think we'll need to. Yeah, if there are 2 atomic orbitals in each unit cell, say phi A and phi B, then we can create 2 different linear combination of atomic orbital states, psi k A, psi k B. So then we'll have eigenstates of that. Yeah. So with 2 orbitals, you create an LCAO block wave function for each orbital. So you have psi ka, which is going to be the 1 over root n r e to the I k dot r phi a r minus r. And you psi k b, which is going to be equal to the same thing, but this time phi b r minus r. Right, and then their eigenstates are going to be a linear combination. So you have big psi k is going to be equal to alpha alpha psi ka plus beta psi kb. Right? Yes. One orbital in the basis? I thought this was 2. Oh, with 1 orbital. Okay, then no. Yeah. I said no. Yeah, I did. I said that. Rewind the tapes. Okay, I said that. Okay. So now for B, we have to calculate the dispersion EK for the one-dimensional crystal shown below. Assume that there is only 1 orbital on each atom with on-site energies labeled EA and EB, and that there is 0 direct overlap between any of the different orbitals. The only non-zero hopping term are those indicated in the diagram. You may leave your final answer into the Hamiltonian matrix rather than simplifying the expression, but you need to also solve for each matrix element. So, okay. So for B, we've got this chain. I'm going to flip to a new page. For B, right, we've got this chain of atoms. We've got a light one, a dark one, going on and on, right? We've got a unit cell, which is A, So we got A, B, A, B. We've got hopping terms. So TAA, TBB, and then from A to hop to B, it's T2. From A to hop to B to the right, it's T1. Okay. And each of these have their own energy, EA and EB. And we have to calculate the dispersion relation, right? So we'll have some large wave function psi k is going to be equal to alpha phi ka plus psi ka plus beta psi kb, right? Because we're going to have two wave functions. So psi ka is going to be equal to 1 over square root of n sum over r e to the ik dot r phi ka r minus r psi kb is going to be 1 over root n phi kb r minus r, right? Okay, now what? Yeah, I have these going on. So it's eigenvalues of the matrix of this. So then we'll need to compute it's e to the I k n a and m a. Why is that the case? Why are we calling one N and one M? I guess R can be written as what? N A1 plus M A2. Alright, so linear combination of that. I guess N times your unit cell phi NA R minus R, right? NA 1 over root N over M e to the I k M A phi M B R minus R. Yeah. Okay. Right, and then we just have to calculate these matrix elements. Right? So what is this? Okay. So phi a to a, right? It's a sum over n and m, e to the minus I k n minus m a, right? Phi a n h phi a m. In this case, we're looking at it hopping to itself, right? Or no, okay. And then this matrix element, so going from m to n, what the fuck? Oh, wait. Okay. So psi a Hamiltonian psi a is going to be equal to 1 over n, and then the sum over n prime e to the I k n prime minus n of a phi a n h phi a n prime, right? Because we're looking at phi a to a, it transitioning basically back to itself. So we're just looking at the hopping term just over n of it hopping to itself. Phi a n h prime phi a 0. Right? Yes. Okay. And so if it's hopping to itself, either what it can have is it transitions to another one, it hops to another one of itself, or it stays still, right? So if it's staying still, then this matrix element is going to give you either just the energy itself, or it'll give you it hopping to another version of itself, which is just going to be TAA. Then it'll be E. Yeah, either n will be equal to 0, or n will be equal to plus or minus 1. In which case this just gives you the energy, okay? Or it can be phi a plus or minus 1, h phi a naught, which will then give you some hopping term. So then this full formula is going to give you 1 over root n, sum over n e to the minus I k a plus e to the IKA. Yeah, okay. So let's start it back from the ground up, right? Okay. Starting it up from the ground up. Now we're working back to the ground up, okay. Snap back to reality. Oh.
You bastard, I'm Marilyn Manson with madness. Now just imagine the magic I like to ask is don't ask for your favorite rapper. Yes, sir. Amen. Church.
Okay, starting it from the ground up, right? Basically, we have, say we have psi A, psi B that we have to describe in terms of these locale wave functions. So one of them is going to be in the n position, e to the I k n times a, because r is just going to be equal to na plus m a a1 a2, but they're equally separated, so that's what this r is going to be for this one. Phi a in the n position, right? 1 over root n summation over m of e to the I k m a times phi b in the n position. Okay, and then we just want to calculate this matrix element psi a, which is then just going to be equal to 1 over n sum of n and m prime of e to the I k n prime minus n a, right? Phi a n h phi a n prime, right? That's what it's going to be. It's going from a n to some new n prime. So for this matrix element, right, we're looking at it hopping from like, we can center where we're looking at from one spot, right? So we can just look at one of the atoms in terms of this, and we can just look at like, okay, either it can hop to another version of itself, or this is from phi a, so this atom a, to another a. So either it can hop to itself or it can stay where it's at. So staying where it's at would be phi a n equals 0, h phi a 0, which would then basically just give you the energy. Or we can say, okay, it can either hop to itself, in which case it would travel a distance of a, or it can hop backwards to itself over here, in which case it can travel a distance of minus a. So it's going to be phi a plus or minus 1 h phi a naught, which is going to be equal to this hopping term, basically. And so now plugging this back into your equation, then you have 1 over n summation now just over n of e to the I k, where n is equal to 0 of a of epsilon a, plus e to the I k, where n is equal to 1 of a, your hopping term, plus e to the I k, where n is equal to minus 1 a, your hopping term, right? So then this is just equal to that summation over n of e to the 0 is just going to be 1, so it's ea plus taa e to the I ka plus taa e to the minus I ka. Boom. So then now you basically pull out all these constants, and then you have that your matrix element is then just going to be ea plus taa e to the ika plus e to the minus ika, which you can then just replace by 2 cosine ka. Would you look at that? Yes. Yes. Okay. Yes. Okay, now we have to do the cross terms, right? So now we have to do, so from this, it follows that psi b of h of psi b is just going to be equal to eb plus tb b 2 cosine ka. All right, it's going to be the exact same thing. Yep. Now the cross terms, the off diagonal terms. So let's do psi b h psi a, right? This is going to be equal to 1 over n psi. Now this time we're taking n and m, a sum over n and m of e to the I k n minus m a, right? And then phi b m h phi a n, right? So we're going to center this at some 0. Just want to make sure I'm doing everything right. Yes, yes. Oh my god, oh my god, oh my god. We're going to center it at some 0. Yes. Yes. So we're looking at a, hopping to some random b terms. We lock it at some a. So with this, phi b m h phi a naught, right? And so now we're looking at centered at this. What can it hop to, right? So it can hop to 2 things. It can either hop to T1 or it can hop to T2 in terms of this. So it has 2 options. So this is going to be phi b1 of h phi a naught, which is going to be equal to T1, right? Okay, I guess you're looking at 0, sure. Oh, in the same cell. Okay, so I guess it is going to be 0. It is going to be 0. So you're looking at it in this, hopping to another position in the same cell, or from this, which is 0, hopping to a position in another cell, which is going to be -1, right? So in 0, 0 is going to be T1, right? And then phi b -1 h phi a naught is going to be equal to T2, right? And then from these two, then you're gonna get 1 over n summation of nm of e to the I k 0a t1 plus e to the I k minus 1 of a t2, which is then going to give you 1 over n summation of n e to the, oh, it's going to give you t1 plus t2 e to the I k a minus. Okay, well, I guess it'll be plus. Okay, I'm just getting a sign wrong here. But the sign being wrong shouldn't matter too much, because either way, I'll get the sign wrong, but it'll just be flipped on the other side or whatever, right? So, yeah, the other diagonal element will come out to be the complex conjugate. Okay. Okay. So let's totally recap the entire problem now. Let's do it from the ground up, from the start it from the bottom to the top. Okay, bottom to top. Oh, okay. Just had to look outside for a little bit, you know, take in life, you know. Major. I just had to look outside the window for a moment. trying to strike a chord, and it's probably C. Sharp major 9, flat, diminished 12. Okay. Started from the ground up, right? So we have to calculate the dispersion for the one-dimensional crystal shown below. So assume there's only one orbital on each atom with on-site energies labeled EA and EB. So there's 2 atoms in this basis, right? So our big ol' wave function psi k is going to be comprised of alpha psi A, beta psi B, where psi A is going to be equal to 1 over root n over the sum, say, n of e to the I k n a phi a n. Psi b is going to be equal to 1 over root n, sum over m of e to the I k m a phi b m. Correct? Correct. Right? And so then we have to solve these matrix elements. Psi a. So in this matrix element is just going to be 1 over n over. So we're dealing from a to a, so we can just do n and n prime, or we do e to the I k n prime. Let's do n prime to n. N prime minus n of a. Phi a n h phi a n prime. I feel like n prime should be on the left. No, n prime should be on the right. Okay. I'm trying to strike a chord and it's probably... Okay, so now from this matrix element, right, basically we have 2 options. Either that we hop from this one, so we're looking at this one, right? So we're gonna center it. First of all, we're gonna center this at 0. So we're gonna say n prime equals 0, right? And now we have 2 options. We can either stay here or we can hop to an energy over here, right? Or we can also hop to one that's over there. So we can stay here, or we can hop here, or we can hop there, right? So in that case, then we have phi a 0, h phi a 0. In that case, that's just going to give us our energy itself because it's staying in its position. Or we can have phi a 1, h phi a naught, in which case it's t a a. Or phi a minus 1 of h phi a naught, which is going to be equal to minus TAA, right? So then put this all together. You have 1 over n sum over n of e to the I k 0a of EA plus e to the I k 1 of a TAA minus e to the I k minus 1 of a TAA. Right, so then this, you have sum of n of EA plus TAA. You factor out e to the IKA minus e to the minus IKA. Or is it plus? Either way, or I guess the hopping term is defined as positive, right? So I guess it won't inherently change with that. Okay, sure. So then we'll have that this matrix element is going to be equal to EA plus TAA 2 cosine of KA. That's that. The other matrix element will be B plus 2TBB cosine of KA, right? And then psi B H psi A is going to be equal to 1 over N sum N and M of E to the I K. Is it M minus N or N minus M? N minus M. N minus M of A phi BM H phi AN, right? And so we're going to look at this. We're going to center our attention over the A and this orbital. So we're going to look at one orbital. So we're going to center our attention at 0, right? So then now we have two choices. Either we go from phi B to its own self, phi A. Not in that case, we get a hopping term T1, right? Or we go from phi B to its negative self in that position in the unit cell from phi A naught, in which case we get T2. So now putting this all together, we get 1 over N sum over N M of E to the I K 0 A T1 plus E to the I K 0 minus 1, which would give you 1 A of T2. So this is T1. So then this matrix element would be equal to T1 plus E to the IKA T2, right? Is it plus or minus? Is it plus or minus? Bruh, it's plus. We fucking did it. Okay, now it makes sense. Yes, because it's N minus M. So if N is 0, then M is -1, then minus -1 is going to give you +1. Okay, boom. And then for the other one, you just take the complex conjugate, which is going to be plus E to the minus IKA T2. Blammo, blammo, blammo. And then you calculate the determinant by doing the characteristic polynomial. The determinant of this equals 0. Right, so this minus lambda, and then boom. And then you'll get what that is, which is... It's not too difficult to diagonalize. Whatever, bro. But okay, that's that. So that's least common. I mean, what is it? Not least common. Linear combination of atomic orbitals. That's what this is. So we just basically, for how many orbitals are in our system, we'd make a Lakau block function for it. And then we just solve matrix elements. And we know if we're really careful about our indexes for like what are these going to be, then we can figure it out. So actually my friend went a little bit overboard with the delta notation. I get what they were trying to go for, but we're not gonna do that. We're just gonna think about it. We're gonna say like, okay, set n equals 0. We're gonna look at 0 hopping to some m. Yeah, and then we just define these n and these m's in terms of these unit cells. So this is n equals 0, m equals 0, n equals 1, m equals 1, n equals -1, m equals -1. And then you can fucking plug and chug. Plug and chug, my boy. Okay. So that's all of 4. Okay, so I feel pretty good about that. So now what? Why are you asking me, bro? Why are you asking me what else? Why are you asking me what's next? Okay, now should be relatively cruising for the rest of this. In the Boltzmann model of a solid, every atom is treated as a classical harmonic oscillator. The Boltzmann model predicts a constant heat capacity at all temperatures. What is this constant? This constant is going to be 3 kb. Or I guess, yeah, it depends on the number of dimensions, so it's dkb. We can find the normal modes of a crystal lattice by treating the atoms as masses on springs, that is, as classical harmonic oscillators. In this case, we would find a temperature-dependent heat capacity. How can two classical harmonic oscillator modes models result in such different heat capacities? One of them, which I think is the Boltzmann model, just uses a isolated harmonic oscillator, whereas the other model is a coupled harmonic oscillator, so they depend on each other. Correct or not correct? Deal or no deal? Yep. At low temperatures, the heat capacity of a metallic solid is known to take the form of this. One of the two terms comes from the Debye model, the other from the free electron gas model. Which is which? The Debye model would just be linear dependence in temperature, and the free electron gas would be the cubic, I think. No, free electron gas. Oh wait, no. Free electron gas treats it as kinetic energy, so then that's going to be the linear. The Debye model, which treats it as like a quantum Fermi thing, is going to be T cubed. Yeah. If we continue to measure the heat capacity while raising the same temperature, the ionic term will change, but the electronic term will stay the same. Why is this? The ionic term, but the electronic term. The ionic term will change because as you raise the temperature, there are more things available for like conducting the temperature. Fermi temperatures are very high. I guess, yeah. So to raise the electrons that are below the Fermi level to the Fermi energy is going to be really, really high. It's going to take a lot of energy. But the ionic term will change because those free ions that are available at the Fermi surface are going to be able to move as you add into the temperature. So that's why the electronic term will stay the same, but the Fermi model will not. The dispersion relation for the acoustic phonons of a one-dimensional monatomic chain is given as this, where gamma is a constant. What are the units of gamma? Well, omega has to be frequency, so gamma has to be frequency. Boom. Got him. So we have to find the three-dimensional density states G omega and use it to write down an integral expression for the heat capacity C. We can just use N. Yeah, so what you would do, right, so you want to find the density of states. So you know N is equal to omega integral G omega D omega NF. Right, you know N is going to be equal to your modes times the summation of K times some occupation factor. But we're just looking at acoustic phonons. The Brionne zone is a sphere. Let the crystal have total. Okay. So then there's going to be 3k, right? Where k is equal to omega over 2 pi d integral of d dk. Right, so this is 3 times your volume over 2 pi cubed times 4 pi k squared dk integral from 0 to k, right? And then you're going to have to perform some sort of conversion of variables, but so far up until this point, am I correct? Yes, I'm totally correct. Except I forgot that k is going to be equal to pi over a, the integration bounds. But yeah, at this point, you do a whole bunch of fucking flipping around, flip it, flip it, flip it. Let's actually walk through it, I guess. Let's walk through this. So omega is equal to gamma sine ka over 2, right? So an omega over gamma is going to be equal to, so sine inverse of omega over gamma, 2 over a will equal k. So for dk, if you just calculate d omega equals omega d by dk of sine ka over 2. So this is going to be omega cosine of ka over 2 times a over 2 is d omega. So then if you know that dk over d omega equals 1. Is that it? dk over d omega equals 1? One over d omega over dk. So you have d omega over dk, which is then just going to be equal to to the inverse. Yes. Okay, yeah, okay. Now you get that. Blah, 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 blah. You plug it back in. Plug. And you can figure out what G omega is. Then you calculate the temperature derivative with respect to energy, but you know what energy would be. Energy is equal to this. Then boom. Okay. Straightforward, relatively so. Oh my god, okay. I can't wait for this to be over.
There's always a crown in rap. That's how it started. Yeah. My DJ's better than your DJ. I'm a better rapper than you. What's the greatest rapper? What are you referring to? You are the greatest rapper. I got you. I didn't. Come on. I'm so passionate about hip hop, man. Like, I don't know where everybody else come from, but when I listen, man. Like, we play house parties, bro, every night. Like, I love it to a point I can't even describe it. You know. And when I heard these artists say they're the best coming up, I said I'm not doing it to have a good song or one good rap or a good hook or a good bridge. I want to keep doing it every time, period. And to do it every time, you have to challenge yourself and you have to confirm to yourself, not anybody else, confirm to yourself that you're the best, period. No one can take that away from me, period. And that's my drive, that's my hunger, I always have. And at this point right now, about the years and time and effort and the knowledge and the history, you know, I've done with the culture and the game I've gotten from, you know, those before me, respect I have for them. I want to hold myself high on that same pedestal 10, 15 years from now. That's what we're going with, so blood control. You're like, I need to say this is what I need. Yeah, what are we doing for? This is culture. This is not something you just play with. You know, get a few dollars and get out. You know, people that admire this music, period. You know, it's my pops in the hood right now that they listen to rap and this is the only thing that can relate to their stories and their tribulations. They live and breathe. You can't play with this. You have to take in consideration what you write down on the paper. If you're not doing it to say the most impactful, or doing it to be the best you can be for the listener to live their life, what are we doing here? There's always a problem.
state counting in crystals. For a d-dimensional crystal containing n unit cells, apply periodic boundary conditions to show that k can only take on n discrete values in the first Brillouin zone. I don't know. K equals 2n pi or n pi x. Okay, you have to show that one wave is going to be equal to another wave at a different position. So this means that this wave will be equal. If that wave is equal to that wave, then e to the ikx at x equals 0 and at x equals n a has to be equal to each other, but at x equals 0, e to the 0 is going to be equal to 1, so you have 1 is equal to that, and you know what k should be equal to, so then you can kind of figure out what, or you know that this has to be periodic, so you can figure out what k should be equal to. Yeah, k and a should be some multiple of 2 pi, so then you can do that. 2 by n. You and your classmates are studying zinc sulfide, which has 3-dimensional crystal structure depicted below. One of your classmates says there are 4 optical modes in the photon spectrum. Your other classmate says that there are only 2 optical modes. Which, if either of them, is correct? Well, you can do that from md minus d, right? So the dimensions is 3. What is m? M? Your modes. No, it's the amount of atoms in your thing, right? Which I'm pretty sure is 1, 2, 3, 4. 3, 4, 12? Is it 12? What the fuck? Yeah, md minus d. Oh, m is 2 because there's 2 atoms in your bases. Okay. M is the amount of atoms in your bases, not the amount of things in your fucking unit cell. Yeah, it's zinc and sulfide. So both of them are wrong. Both of them are idiots. Both of them are fucking dumb as fuck. The diamond cubic structure consists of FCC lattice with 2 atom bases. How many atoms are in the primitive unit cell? It's a 2 atom basis. So 2 atoms? How many atoms are in the conventional unit cell? Eight? I am correct, because this is what I was thinking. Where's the picture? I was thinking, okay, this is gonna be how diamond look in FCC. It's just a zinc part. So in the primitive, right? This is the primitive thing, right? And if there's 2 atoms in the basis, then in this primitive thing, there's gonna be 2 atoms attached to it. So if you're taking it to the full thing, there's gonna be 2, 4, 6, 8. And for some reason, the freaking robot on my phone activated, even though I didn't even say its name. It's really annoying. I mean, it is legit listening to you every single time. It's probably reporting it to all your social media as well. It is what it is.
Drake, yo, because this is after Kendrick just dropped. I said, bro, you just need to give me the heads up of what's gonna be what. Because you know I gotta make sure I'm at the right spot. And right now I'm not in the right spot. And he says, yo, you got 30 minutes. Get on stream. And I'm like, this is the I think 50's still on stage. And I'm like,
and to set the stage, just Drake has told us he's dropping the nuke at this point.
Yes.
So he says you got 30 minutes. I'm dropping the nuke.
Yo, I looked at everyone around me.
Yeah.
In any dimension, what relationship do real space primitive lattice vectors AI have with the reciprocal space lattice vectors? BJ uses relationship to construct primitive reciprocal vectors of the two-dimensional lattice defined by that. So you know AI.bj is going to be equal to 2 pi delta ij. Or AIBI. No, AIBJ is equal to 2 pi delta ij. Yes. So for A1, B will be orthogonal to this. So you know B1 or B2 because AI.bj. So A1.B2 has to be orthogonal to each other for delta ij to be satisfied. Right? B2y. Yeah, I did this pretty explicitly sometime. What was it? What was it? What was it? This is going through the previous midterm. Yeah, AI.bj is equal to 2 pi delta ij. So you know that A1.b1 equals 2 pi, so then b1 is equal to 2 pi over A1. Or no. Or yeah, A2.b2 is equal to 2 pi. So you just, b2 is going to be equal to 2 pi. Okay, I guess first things first is that you know that A1.b2 has to be equal to 0, right? So then they're orthogonal. So you know that b2 is going to be orthogonal to A1, which is the y direction. So you know that b2 is going to be equal to b2 in the y hat direction, and you dot that so you can figure out what b2 is. Then b1, you can write it as a linear combination of b1x and b1y. You can dot them, figure it out. I don't want to write down this. I don't want to work through this, but I should work through it. Okay, so you know AI dot bj equals 2 pi delta ij. A1 equals x hat. A2 equals s over 2x hat plus s root over 3 over 2 y hat. So automatically, you know that A1 dot b2 has to be equal to 0. So then b2 is orthogonal to A1. Therefore, b2 is equal to b2 y hat, which is orthogonal to sx hat. Right, so then you can calculate a1 dot b or a2 dot b2 equals 2 pi, so then b2 y hat dotted with s over 2 x hat plus s root 3 over 2 y hat is going to be equal to 2 pi. Well, this is just going to leave you with s root 3 over 2 b2 y hat equals 2 pi. So then b2 y, or b2 is going to be equal to 2 pi over s root 3, so times 2, which is going to be 4 pi in the y hat direction. Yes. And then you can write b1 as a linear combination of x and y hat vectors. You know that a1 dot b1 has to be equal to 2 pi, so then s x hat dotted with b1 x hat plus b1 y hat has to be equal to 2 pi. So this is just going to give you s b1 x hat is going to be equal to 2 pi. So then b1x is equal to 2 pi over s. So then now you can figure out what b1y is. How do you figure out what b1y is? I guess you can use that a2.b2 will be equal to 0? Oh no, a2.b1 will be equal to 0? So then s over 2 x hat plus s root 3 over 2 y hat dotted with b1 x hat is equal to 0. So then you have s over 2. So it's going to be pi x hat plus s root 3 over 2 b1 y hat is equal to 0. So this is equal to negative pi x hat negative 2 pi over s root 3. Wow, I did that. I really did that. Negative 2 pi over s root 3. Damn, bro. I really just did that. I still got it. I still got it. Yeah. Numero 5. Numero 5. Oh. Electron hole, like, oh, the conductivity. So you know energy, right? Energy is going to be equal to E naught plus AK squared plus dot dot dot. Right. So then you have that AK squared is equal to H squared K squared over 2m. The effective mass of sigma is going to be equal to where m star is defined by that. Correct? I know I'm correct. Bro, just tell me. Yes. Boom. That's defining the effective mass, and then your sigma is going to be equal to that. Boom. If the density n in the electron light case is equal to the density p in the whole light case, would the conductivities be the same or different? They'd be the same? Right? Yeah. Would the Hall conductivities be the same or different? They'd be different. Yeah. You're just setting them equal to each other and then calculating some shit. Okay, guys, that's about it. We're done. We're done. We're done. We're done. Yeah, but we're done. All right. Okay. Okay, guys. Okay. So what did we learn today? We learned the least common atomic orbital thing. Should we even look at this? Derive the dispersion relation. You start off with the equation of motion. So to derive a dispersion relation, you start off with the equation of motion. You have an ansatz equation where x is going to be equal to this. Therefore, if you solve for this, yeah, oh, therefore the double derivative will be equal to that. Plugging in the double derivative. Then you can derive the dispersion relation. Okay, deriving dispersion relation, relatively straightforward, I guess. Start off with the equation of motion, right? Write down what the force is going to be. This is the spring constant due to each mass, right? So then you get that when you work it out. Then you make an ansatz. This, which equals that. Which then you'll get this. Yeah, once you plug it in, and then you just boop, 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 boop. You'll have an omega somewhere in here, somewhere here too. You'll be able to cancel out all the e's, and then boom. Yeah, something like that. Something like that. Okay, that's how you derive. That's for deriving the dispersion relation. You'll have some picture of what's going on. Yeah, then you just do this. Good thing we checked that out. That could be on the test. Okay. Peace out, guys. I'll see you tomorrow. Or maybe I won't see you tomorrow. Maybe I will. I'll see you for more dubs, more victories on the way. We got more victories on the way.